We want to look at the substrate first. Okay? That's going to be our primary difference between our SN1 and our SN2 reactions. In the SN2 reaction, because we had that backside attack, we're looking primarily at steric hindrance affecting it, which means if we jump from what we should learn or remember from our SN2, from our substrate, we can look at patterns of this, and we would expect our methyl groups to react faster than our primary, faster than our secondary. The tertiary substrate is so sterically hindered that it will not react in an SN2 reaction, which means if you see a tertiary alkyl halide, what does that mean? It's going to be SN1. It cannot go under SN2 conditions. Okay, so we've got some way to eliminate one mechanism versus the other by looking at that substrate. But what if you have a secondary substrate? Well, that works in both mechanisms, so the substrate doesn't help you then. So that's when you could move to the next step, the nucleophile. So look to the nucleophile strength. In an SN2 reaction, it must be a strong nucleophile for it to function. What makes it a strong nucleophile? That negative charge. So look for a negative charge. That negative charge can be hidden. Okay, where can a negative charge be hidden? Nope. Is this a strong nucleophile or weak? Strong because negatively charged. So what I'm asking is where can I hide that negative charge? If I put a hydrogen on it, it's not negatively charged. But what happens if I put a metal next to it? What's the bond between a metal and a nonmetal? Ionic, which means by definition, when we put this into solution, we get sodium ions and our negative oxygen. So the metal can hide that negative charge. So if you see a metal, you're looking at a strong nucleophile again. Okay? When we move to SN1, you'll notice that it says weak nucleophile and it's not bolded or anything like that. Why? Because we don't care about the strength of the nucleophile, period, in an SN1 reaction. Why not? When we look at our mechanism to determine the rate, it's only dependent on the concentration of our substrate. So we could care less about the strength of the nucleophile. Both of them need good leaving groups, so we can move on from there. We already talked about the substrate pattern. If our substrate and our nucleophile don't give us any tips as to what's going on, then we can shift to looking at the solvent. And the solvent can then change certain dynamics. Okay, under an SN2 conditions, we would expect the polar aprotic solvent to work best. Under SN1, we want the polar protic. Okay? If you are given no other option but to evaluate based on the solvent, then feel free to analyze your answer based solely on the solvent. But the solvent is a very tricky thing to play with. Okay? So unless you are forced to decide between SN1 and SN2 based solely on the solvent, analyze it based on the nucleophile strength or the substrate. Okay? Complications or extra things to worry about with stereochemistry in the SN2 reaction, again, because of that backside attack. If we start with a stereocenter, we're going to end with a stereocenter as well, but it will be an inversion in stereochemistry, most typically. If we're looking at an SN1 mechanism, because our very first step generates that carbocation, where we now have lost our stereocenter, where it can look at our nucleophile coming in either from the top or the bottom, generating both possible products, both R and S. So typically when we look at an SN1 mechanism, we refer to that as just forming racemic mixture. Okay, that's the theoretical. In actuality, you do see some kind of favoring more for the backside attack, more for that inversion, and that's just kind of what's happening in solution. When we look at our rates, one kind of important point that we can address here just to make it complicated, though you should remember this in theory from 152. What do the brackets mean? Concentration. So a nice fun question to ask about rates is what happens to the rate of, let's pick an easier one. Let's look at the SN1 mechanism. What happens to the rate of the SN1 mechanism when I double the solvent? The reaction slows down.
Oh, yeah.
Why does the reaction slow down?
Changes concentration.
Remember, concentration is units of moles per liter. That liter is dependent on your solvent. Okay? So if we start changing the amount of solvent present, that will also change the concentration. If our concentration changes, the rate changes. You should be able to go through and look at that and quantify exact changes with each of those solvent changes. Okay? So for the instance of our SN1, if we double the solvent, what happens to the rate? The rate decreases by a half. What happens in the SN2 if I double the solvent? Decreases by a fourth because the solvent shows up in both those concentrations. Okay, so it would be a half times a half. Kind of, sort of. That is a very popular question to ask because it comes back to rate laws and comes back to understanding everything about chemistry. So you do see a lot of 152 stuff show up in that kind of situation. The very end of Chapter 7, I think it's Chapter 7, is thinking about retrosynthesis. It's a bit of a jump to start talking about retrosynthesis at this point, because the idea behind this is how did we make a particular compound? So we would have to work backwards and decide what things could potentially change, which means we really have to have an understanding of all the possible reactions or places that it could have come from. Well, how many different reactions do you know? Okay, 3 at best. I would almost argue it's only 2. You have acid-base and substitution. You know 2 ways to do the substitution, but you still only know substitution. Okay? When trying to evaluate your retrosynthesis, you need to look at your product and look for possible sites of reactivity. What do I mean by possible sites of reactivity?
What carbon is going to change?
I would say it's even less specific than what carbon is going to change. When we run an acid-base reaction, what do we need to find? We need to find a proton, which is a positively charged hydrogen, and a negatively charged base. When we run a substitution reaction, what do? We find a positively charged substrate and a negatively charged nucleophile. What are we trying to identify in both those circumstances? Charges, positive and negative. What happens in the course of generating that product? We now have a weaker positive and negative, but we still have that positive and negative. So if I want to look at this product and try and decide, how did I make this? What I need to go through and do is identify where's the easiest place to make or break bonds, which is going to be right around where I see those positive and negative charges. Okay? So let's take a look. Don't fail me. Come on. How about that carbon-hydrogen bond? Is that a good place to start looking for a possible starting material? Why not? There's no positive and negative charge within that because there's no difference in electronegativity. Okay, so that doesn't make sense to think about for our retrosynthesis. Where's our other option? We could look at the OH bond. That's a good possibility. I could cleave that bond, in which case, what did I supply? I needed to react H plus with, I won't be lazy, O minus with all that other junk. There's the other junk. That almost looks like my signature. That's a bit depressing. Okay. So that is one possible synthesis. We found a polar bond. We broke that polar bond, went back to what those starting materials were, and said, hey, there it is. Okay. Depending on what we might be starting with, we might want to get a little bit more detailed and say, well, we can't have O minus, so we'd have O and sodium. Okay. We've now temporarily stabilized it. We can't have H plus on its own, so we might go through and say we have H2SO4. Why would I pick H2SO4 and not say something like HCl?
Chlorine might interfere with.
Chlorine's a nucleophile. H2SO4 doesn't have a nucleophile. Okay? So we have to start evaluating the reagents that we use and make sure that we aren't going to add some secondary reactivity to our reaction. Okay? Yes?
Doesn't that OH have to be protonate for it to be So if you did try to do this backwards, was what you've drawn really valid?
The OH has to be protonated. I'm not sure where you're going actually with that. Try that again.
Well, I was just thinking that wouldn't you need something more like hydronium to do that?
Are we trying to get the OH to leave?
No, but if you're doing it back, if it's there and you're trying to go backwards.
What bond are we making? We're not trying to put an OH bond on there. What we're trying to do is put on
Just hydrogen.
just the hydrogen.
Oh.
Okay? So you're right. If we looked at the alcohol chemistry, we have a problem. We haven't done that yet. That's going to actually be the next step of this.
So okay.
Okay? Was there another polar bond that we could have looked at?
And the CO bond.
We also have the CO bond. If we were going to go through and break that bond, what would we need to react?
OH minus is the nucleophile.
We got OH minus as our nucleophile, and, oh man, I think I'm going to have to draw this one out.
Plus.
Can't just use my signature. What charge does that carbon need to be? Have to be positive to match up with that negative oxygen. Okay. So all we've done is cleaved and said, okay, this is something that possibly works. Okay, now we've got to decide, is this a valid step? Okay, can I generate OH minus? Is that something I can supply? Yeah, how could I supply that? I could go NaOH. Nice and simple. Now let's take a look at the cation. Is that something I could easily supply? What's the issue with that cation?
It's not stable.
It's very, very unstable because primary, which is a positive charge as well, but we're looking at a primary positive charge as opposed to secondary or tertiary. I'm going to come back to that in a second. We need to stabilize that positive somehow. How could we stabilize it?
Move it to the other carbon.
We could move it to the other carbon, but then where does the OH attach?
The other carbon.
The other carbon, is that what our product was? No. Okay, which brings up an important point with this reaction. That cation, number one, is it stable enough to form? Probably not. It's the primary. Go back to that previous, I'm going to now just delete all my drawings. If we look at our SN1 conditions where we do have the possibility, okay, for rearrangements, do we form primary carbocations? No. Right? Which means I don't need, oh man, I really do have to draw it all back out. We got our CH3, CH3, CH2. I cannot form that as a carbocation, but that carbon needs to be partially positive. Okay, how can it be partially positive?
The broom.
I need to have something taking electron density away from it. We can put on a halogen. Which halogen? Who cares? Bromine's pretty standard, so we can stick with bromine. Okay? Because that's a primary position, and I don't want rearrangements, what mechanism must I run under? SN2, which means when I supply that OH, it had better be supplied as a strong nucleophile with the sodium. What if I had supplied that OH as HOH? It's a weak nucleophile. If we even suggested that this reaction could potentially occur, which it couldn't because we'd form a primary carbocation, we'd get a rearrangement, not making our product. Okay? So you cleave the bond, look at the pieces, and then start to decide what mechanism does this have to run under. How can I get each of those pieces into a pseudo-stable state? Yes?
What's the primary?
Primary versus secondary versus tertiary. What does primary mean? It's attached to one other carbon. So when we look at, do I have the halide? Yep. So when we look at our halogens, the classification is that first off we've got a halogen bound to a carbon. And if we're going to then go through primary, secondary, tertiary, our halogens can only be bound to one carbon. So we won't define it there. We'll define it at the carbon to which our halogen was attached. It's only attached to one carbon, so it's primary. And if we move to that middle carbon, it's connected to three other carbons, so we've got tertiary. Okay? So when you're looking at synthesis, start picking a bond, cleaving it, go backwards and see what you could do with it. Okay, in this case, we could have done two types of reactions. We could have run the acid-base, or we could have run the substitution. Okay, which one do you think is typically being asked for? The substitution. Okay, so if the question is very vague, you can get away with sneaking in an easy one by just saying it's the acid-base reaction. Hey, I'm done. Okay. Usually what will be asked is multiple steps, in which case you can't just run the acid-base reaction. Okay. So be aware of that and start considering that when you look at a structure. Start to say, okay, what bonds can break, what bonds shouldn't break, how can I work backwards? Okay. I know, we barely just talked about moving forwards, and now I'm asking you to think about walking backwards at the same time. Okay. Questions about Chapter 7? And no, I won't do it all again. Okay. Based on the homework, you should have finished 15, 16, and 17. All three of those homeworks, you have had the background to be able to answer all of those questions, I'm pretty sure. I don't think elimination showed up in 17. Which means you should be done with all of that by this point. Okay? Yeah, I've definitely reviewed that. I know that's not true. Okay? So please start getting caught up. You will find that if you have to try and cram in substitution, homework, elimination, homework, and studying for the exam, it's not going to go well for the exam score. Okay? So, Chapter 8. We're looking still at the alkyl halide functional group, but now what we're going to do is look at eliminations. Okay, so we evaluated our Chapter 7 substitution reactions, which is that top one. What's the bottom one? We've got an elimination. How do we know it's an elimination? Look for, and I wouldn't call it a double bond, I would call it instead a pi bond. Why? Yes, we are talking about the p orbital. Does it have to be a double bond? It could have been a triple bond. Okay? So we can still do those other types of eliminations to generate any type of pi bond. So you have to be careful with classifying it as just a double bond versus a triple bond versus, for that matter, even a carbonyl. Okay? So we're looking at the formation of a pi bond. Why do we call it an elimination if we're looking at the formation of a pi bond? Sort of. When we say leave, what does leave mean?
Removed from the main.
It takes electrons with it. So anything that leaves the structure, by definition, takes electrons with it. So our leaving group did what to the electrons in that bond? It took them with it, which meant what charge started to build on that carbon? Right, if I'm going to form my pi bond, what do I need? I need electrons. Where are those electrons found? Looking at the base. That would be a nucleophile attacking your positive charge. That's not an elimination reaction. We're not using the electrons on the base for your elimination. We're using the electrons found from a hydrogen. Okay? The hydrogen does not leave the structure because it doesn't take the electrons with it. We take the electrons away from the hydrogen, so now it can't be attached to the structure. Okay? If anything, our substrate leaves the hydrogen, okay? Which just sounds all sorts of weird. Okay? But what we're talking about is eliminating the hydrogen, which has what charge? Once it's left, positive charge, what did the leaving group have? A negative. Altogether, we eliminated that small molecule. So in an elimination reaction, what we're referring to is a small molecule being removed. So in this case, hydrogen bound to the leaving group. Does it necessarily mean that our product is going to have exactly that bond patterning? Not necessarily. You'll notice that we've got the leaving group and the hydrogen bound to different species within our product. Okay? It just so happened when they first discovered this reaction, they saw the formation of water. Water was eliminated from the molecule. Okay? So the names sometimes make sense, sometimes don't. So substitution, what are you looking for? and change of groups. I remember that change of groups does not have to be a single atom. It could be a massive structure. But what you're looking for is just the change in connectivity between carbon and some other species. When we move to the elimination reaction, what are we looking for? Formation of that pi bond. Okay? So our basic elements within the elimination, you'll notice that we have a lot of very similar things. We've got substrate, whatever's containing our leaving group. We're going to have our leaving group, which also has to leave. In the case of this chapter, our leaving group is going to be any one of the halogens. Why? We're looking at the alkyl halide reactivity, so it makes sense that we're looking at those halogens. We're still going to have a solvent. You'll notice that I struck that out. Why would I strike that out? It really doesn't play an important role in determining your elimination mechanisms. Okay, so you can evaluate it, but when you look at how a solvent plays a role in the substitution reactions, it's pretty important. When you look at it in the elimination, it's really, really misleading to actually evaluate it and decide which type of mechanism you've got. Okay, so be careful looking at your solvents. The biggest difference that you're going to notice is that in an elimination, the number one thing that you do not have is a nucleophile. Because if a nucleophile is present, what would happen? Substitution. What we're going to have instead is a base. Anybody see a problem with distinguishing between a base and a nucleophile? They both have non-bonding electrons. For all intents and purposes, their definitions are almost identical. Okay? That's what makes this very tricky. And we talked about that delineation between nucleophiles and bases way back when we first talked about nucleophiles in the substitution chapter. It's going to come back and play an important role here. We have to be very careful that what we're looking at is a base and not a nucleophile. Okay? So when we're looking at our bases, what they'll be doing is donating electrons to a hydrogen, okay, removing the hydrogen from the structure, and then we can get our pi bond formation. Okay? You'll also notice with both the base and the solvent that you see E1 and E2. What do you think those are going to be referring to? Elimination type 1. What's the type 1? Unimolecular. Where did we see 1 types before? In our substitution. Turns out the SN1 and the E1 follow nearly identical reaction pathways or mechanisms. The E2 stands for elimination type 2, where the type 2 means bimolecular. Effectively the same thing as our SN2. Okay? Anybody see a potential issue popping up with this? We're going to see not only competition between the two, so for an individual set of reagents, we might actually get a mix of possible products. But not only that, when I talked about SN1, you say, okay, I understand SN1. Now E1 is also reacting at the same time. So it's not just what's the difference between SN1 and SN2. It's what's the difference between SN1, SN2, E1, and E2. You have 4 different things that can all possibly happen at the same time, and those 4 different things are controlled by the same 4 different things. Our substrate, our leaving group, base versus nucleophile, which again we said was effectively the same thing, and our solvent. Okay? So you have to weed through these 4 possible variables and decide which mechanism makes the most sense. Okay? And yes, there are certain conditions where if you're given those conditions, you get virtually all reactions, almost all, 3 out of the 4. Okay? So you have to be aware of what those conditions mean and how they go through in process. In theory, you should be happy with your substrates and your leaving groups and also with the solvents, so I'm pretty sure we're going to skip those and just jump straight to our base situation. Okay? Bases are going to donate electrons to a hydrogen, so they're going to remove that hydrogen ion from whatever your substrate is. Okay? So if we take a look at our standard acid-base reaction, here we go. Okay? Our base hydroxide is removing a hydrogen from our alcohol. Mechanistically, what are we saying happens? Where's our arrow start? Where are our electrons? On the base. Where's our base? The negatively charged OH is going to act as our base because it has the most electron density, the most reactive. Those electrons are going to share with the hydrogen. How many bonds would that hydrogen now have? 2. How many bonds can hydrogen have? 1. So what has to happen? We're going to have to break a bond. We can either break the bond we just formed, in which case that was a waste of an arrow to draw up in the first place, which I do sometimes, but okay. Or we can break the other one. So we'll take the electrons in that bond and we'll move them where? Why to the oxygen? You weren't specific enough. Which oxygen needs to take those electrons? Why the one to the left? Okay, I can trust the instinct. I like that. The one on the right's wrong.
Elimination reaction.
If we move the electrons towards the right, that oxygen would have too many electrons. What would happen to the oxygen on the left? It would have not enough electrons. The electrons are going to have to go to our oxygen on our left to generate our product. Okay? So what we're trying to do is evaluate where that electron density shifts and sits. What's going to determine how it shifts around? What's the most negative? What's the most positive? What's the most electronegative? Okay? So when we're looking at electron density in a bond, the electrons are going to go towards which atom? The most electronegative. Why? Because that's the definition of electronegativity. The ability to hold bonding electrons. The electrons are already naturally drawn that direction. Okay? What happens in this case? Trickier one. Not quite sure it's the one I wanted to show, but so BR's gone. What does that mean the BR is going to do? It's going to take the electrons. So all we're going to try and do in this case is come up with a rough idea of what happened. We aren't concerned necessarily about how many steps or any of that. We're just going to kind of push through this as quickly as we can. So the BR has to leave, which leaves what charge on that carbon? Okay, a positive charge. So what I'm doing is showing that in blue because I'm just trying to note it so that I know what's going on. I've got a positive charge there. Where is that carbon in the product? Is it this one? Probably not. I can accept that. The one with the triple bond. Which one with the triple bond? On the right-hand side. So what we are looking at is that carbon being that one. Okay. What happened to that carbon?
Took electrons from the hydrogen.
It had to form another pi bond. To form that other pi bond, what does it need? Why does it need electrons?
Because that's what a pi bond's made from.
Sort of. The charge is positive. It needs electrons. Okay, the electrons have to come from the hydrogen to make the pi bond because that carbon doesn't have any electrons. That's why it's positively charged. So sort of mechanistically, will come from that hydrogen bond to form our pi bond. Okay? And there we've kind of made our product. Anybody have any issues with what's drawn up there that you can put a question to? Yes.
Okay, I'm kind of confused because the water,
Yes.
the HBr,
Yep.
it received its hydrogen from the water group, and then so that would leave an alcohol, and then it had a negative charge.
So you'll notice that we've had all sorts of weird things happening in here. I did not show water do anything. Okay, what is that water acting as in this case? Solvent. True. What else is that water acting as? It will act as a base as well. Why would it act as a base and not, say, Br minus? Why would water act as a base and not Br minus? One of those potential answers is sitting on the other side. What is HBr?
Acids are stronger.
a strong acid, which means by definition it does what? Dissociates into H plus and Br minus. Is Br minus actually something that's actually going to take the hydrogen off? No. Why? Because that makes a strong acid. Strong acids, by definition, dissociate back into their ions. Bromide's not going to act as the base. So what's going to act as the base? Water. Okay. So if we were really going to draw out our products and get kind of nitpicky with the details, HBr would be a bad thing to draw. And what we would expect to draw is Br minus and H3O plus. H3O plus is a pretty strong acid, right? Is it as strong an acid as HBr? No. So H3O plus, as far as this goes, is the more stable form to use. Okay. Why do we not typically care about the Br minus or the H3O plus? That's not the organic compound. Okay. So if you're asked to draw everything out, you need to evaluate the charges of the secondary species, so your bromide and your H plus, okay, and potentially your solvent, and try and decide what's the best conformation for them. If you're asked to draw the product, do we care about those secondary species? Nope, because they're not organic. Okay? So when you go through a reaction, evaluate the organic product first, try and decide what's going on with it, address those. So in the course of this reaction, that blue curved arrow, what type of reaction happened there? An acid-base reaction. To perform an elimination, what do we also need to do? An acid-base reaction. It is part of the elimination mechanism. Okay? Yes?
Is it typically shown the hydrogen that's going to end up being eliminated? It's like normally they're not.
So yeah, deciding on whether or not that hydrogen is actually going to be shown. Typically, it is not shown. Why do we typically not show the hydrogen? A couple reasons. We can be pessimists and say that gives the answer away. Hydrogens are part of those implied reactions, so we typically don't specify the hydrogens. Okay, so you've got to watch out for that within the elimination reaction. Where did that hydrogen come from? It came from the atom that was next to our leaving group. Could I have pulled a different hydrogen off of this structure? There's another atom next to my leaving group, but does that atom have any hydrogens? No. Okay. So we wouldn't predict any other eliminations. In this case, we're going to get that one case. Okay? Kind of, sort of? Kind of, sort of. Good. Nucleophile versus base. Your nucleophiles donate electrons to anything other than hydrogen. Bases donate it specifically to hydrogen. What we're looking at is a steric or size role in this. If we look at a relatively small species, that small species can get in to attack atoms that are typically buried inside the structure because there isn't a whole lot of electron repulsion. So the smaller our species is, the better it will act as a nucleophile. Right? Well, if we want to do an elimination reaction, what do we want? Nucleophile or base? Base. So we want to make sure that that species has that negative charge. It can act as a nucleophile. But make that negative charge as inaccessible as possible. To do that, we'll add a lot of bulk to that structure, and what we'll end up with is our classic base, the one in the lower right-hand corner, also referred to as, it is an alkoxide, but so is the one on the left. T-butoxide. T-but for the T-butyl alkyl group, and the oxide for our negatively charged oxygen. Okay, so if we're going to try and pick a classic base, T-butoxide is probably the most frequent one you will see. There are other ones that show up. You got DB, did we say that was U or N? I don't remember. DBN. So we got DBN up top as another possibility. Okay. Another good strong base that acts pretty much exclusively as a base, This one's kind of frustrating because it's typically written by its symbols instead of by its formula or structure. LDA, pretty good base. What is LDA? Lithium, a metal, diisopropylamine.
That's what I was going to say.
What charges are nitrogen? It's negatively charged. Why might we expect that species to act only as a base? Why is it not a strong nucleophile? It's negatively charged, but both of them are negatively charged. It has to do with size. The isopropyl groups act as a steric blocking, preventing the nitrogen from actually getting in and attacking anything other than a hydrogen. Okay? So, in this elimination chapter, if you're told to do an elimination, you don't need to evaluate whether you have a strong base or a nucleophile. Okay? If you're told predict the product, now you got to be careful. Okay? Because if your structure acts as a nucleophile before it can act as a base, or it acts as one or the other, you're going to have to look at that other possible reaction as well. Yes, Diego.
So the one on the very left, that would be the nucleophile, right?
The one at the very left would act nicely as a nucleophile, but unfortunately it will also act as a base. Which reaction is easier to do, acid-base chemistry or substitution elimination chemistry? Which reaction did you do in all of your Gen Chem background? Acid-base. Why? It's easier to do. It's easier and faster to go through and do. Okay, so if you're given the option to run an acid-base reaction versus a substitution elimination, you almost always push that acid-base reaction first, evaluate the result, and then push further if you need to. Okay? Elimination. Now what we can do is get into the mechanism. Oh, whoops, I gave you some information. What bonds were broken? What we should do, as always, is compare across the reaction and try and decide what things changed. Okay, we broke the carbon-halogen bond. We also broke the carbon-hydrogen bond. And then at the same time, we formed the pi bond. Based on what we've talked about so far, is there anything I've left out? Say, maybe from that previous slide. Base. Why did I not list the base in this case? It's not attached to the product. Okay, so when we're concerned about trying to predict a mechanism, what we're going to focus on is our substrate and it getting towards the product. The elimination does not necessarily have to have that base present. So what I'm focusing on is just the bonds that are changing within the substrate getting to that exact product. Okay. Next, simplification. And this will become more important when we look at the addition reaction and also show up in the elimination. What bonds should I look at when I try and decide the mechanism? Because already this is going to get more complex than our substitution, because I got 3 different things going on as opposed to 2 with our substitution. What about that pi bond? Should I look at that or not? Should I look at the forming pi bond? We won't look at the forming pi bond at all as far as our mechanism goes. Which seems a bit odd. Why can we ignore that? Can I draw a resonance structure for my product? Doesn't have to be good. Can I draw a resonance structure? To draw a resonance, what do we need to have? Lone pairs or pi bonds. Do we have one of those things? Yeah, we've got the pi bond. So what we're going to do is take a look at that pi bond and try and move it somewhere else. Since I don't know what bonds are hanging off of that, I'm not going to move my pi bond bond to bond. Instead, I'm going to move it bond to atom. And I'm going to take that pi bond and take those electrons and put them on that carbon. What's the result? A negative charge on one carbon, or a little smiley face, and a positive charge on the other. Why go through and show this? What's the relationship between those two structures?
One stable, one negative.
They're resonance structures, which means they both exist simultaneously. Do I have a pi bond in my bad resonance structure? No. So, should I look at the pi bond forming? No, because it doesn't necessarily have to form. I could just as easily, if we go back to our starting material, go through our basics of what has to happen. We said X needs to leave, which puts what charge on that right carbon? Positive. What was the next step of our reaction? We had to take the electrons in that C to H bond and we moved them to the pi bonds. We went from bond to bond. Did we have to go bond to bond? We could go bond to atom, which puts what charge on that carbon? Negative. What have I just drawn? That resonance structure where there was no pi bond forming. Okay, I know that was an awful lot of work, but what did we end up doing in this case? We took a reaction that had three things happening to it, and now we can go through and evaluate the mechanism based on two things. We are looking at breaking that carbon-halogen bond and breaking that carbon-hydrogen bond. Those are the only two things that I have to evaluate. What are the possible ways that we could go through and do that?
Taking the electrons from the bond, from the carbon-halogen bond.
We can take the electrons away from the carbon-halogen bond first. Then we can take the electrons out of the carbon-hydrogen bond and put it onto our carbon. There's our first step. What's the second step? Or a second type of mechanism? What's that? No, you had the right idea. You could take them out of the hydrogen bond first and then break the carbon leaving group. That one gets a little bit trickier to go through and evaluate, and depending on how you draw those arrows, we could potentially draw that as a mechanism. Okay? It's not going to work because we can't form the pi bond at that same time. Why not? The leaving group hasn't left. So that would be like the third type of reaction that we had with our substitutions. What's the second type? We break and form all at the same time. Did I put those down? Yeah. So we've got all three of those possible options. Okay? And you'll notice that as a result of each of those actions, we end up forming the pi bond. Okay? And the step 3 isn't going to work very well because we would end up forming the pi bond before our leaving group left, and that doesn't work. Okay, so we're again back to these two mechanisms. You'll notice that these two mechanisms have very similar relationships back to what we looked at when we looked at substitution. In E1, we got rid of the leaving group, nucleophile came in and attacked. What happens in our first option? We get rid of our leaving group, and then our electrons come in and attack. It's effectively the same thing. What happened in the second step, or the second mechanism? We did everything at the same time. The leaving group left, electrons came in and attacked. Okay? The only difference between the elimination and the substitution is the source of the electrons. Where's the source of the electrons in a substitution reaction? From the nucleophile. Where's the source of the electrons in the elimination? From within the substrate. It's the bond between the carbon and hydrogen. So if we change the source of electrons, we change the reaction. Okay? So let's go ahead and take a look at an elimination. Okay, based in the unimolecular type, so I'm already giving some hints away. We're going to break our carbon leaving group bond first, and then we'll go through and form the carbon-carbon double bond by getting rid of that hydrogen. How do we show our arrows for breaking that bond? We'll start the electrons at the bond and have them go to the leaving group. Okay, remember our first step is the leaving group must leave. Okay, what's the result of that? Whoops, that was not supposed to happen, but there you go. Now it's all drawn nicely for you. Our result is that we have that carbocation and our leaving group. Okay, now what has to happen? We're going to look for a source of electrons. We don't have a source of electrons outside the structure, no nucleophile, which means we have to find that electron source somewhere within the structure. So what we'll do is move to the next atom away and take the electrons away from that hydrogen, and move them towards our pi bond making, or towards our cation making the pi bond. Okay. The result is our final product. So 2 steps. Okay. Within these 2 steps, which one do you think is the slowest? Probably the first one, making that carbocation, which means the primary thing we're concerned about with an E1 type reaction, the stability of the carbocation. What was the most important step in our SN1? Stability of the carbocation. What's a massive issue between the SN1 and the E1 reactions? Not only are they very similar, they compete with each other, directly compete with each other. The slowest step of both of those reactions is that first one. So what we are now looking at is a fast step in both cases that they're trying to run through. Which means if you are given conditions that suggest an SN1, but I say predict the products, you should give me the substitution product and the elimination. Okay? Both are possible products. Would we expect the elimination to occur as fast? I'll come back to you. What is the elimination last step?
It has to eliminate the hydrogen.
It has to take the electrons away from the hydrogen. Okay? Just like our leaving group took the electrons away from the carbon. Why did the leaving group take electrons away from the carbon? Our leaving group was more electronegative than the carbon, which meant it could take the electrons away. So let's go down and evaluate that same relationship here. We're looking at hydrogen versus carbon. What's the difference in electronegativity? Hardly anything. Is that an easy bond to break? No. Okay, so we would expect the elimination reaction to run a little bit slower because it is trying to break a much more difficult bond. Okay, now back to your question. Sorry.
I mean, would you have to determine how, like, if you'd have to give both products, but then you'd have to determine which one is more likely. Could you really do that?
Depends on the conditions given. We'll talk about those conditions. Other questions on this mechanism?
So then, how are you supposed to be able to tell whether it's going to be in
Or an SN1?
Yeah.
We haven't talked about those conditions yet. So there is one extra little hint that we can kind of push into, which has to do... not sure that's the image I wanted, but it'll work. Okay, what's happening in that elimination is that we've got our carbocation. Our carbocation has what hybridization? If we look at the hybridization of that carbon, it is sp2 hybridized, which means there's a leftover p orbital. What is occupying that leftover p orbital? And yes, there were air quotes for those of you listening at home. Kind of nothing. A lack of electrons, also known as a positive charge. Our carbocation's reactivity is all centered around that pi bond. What is special about that pi bond? What can I put into this side of the pi bond? Sort of. Get a little bit more specific than anything I want. Electrons. What can I put in this side? Electrons. Okay, so for this reaction to work, we have to be able to dump electrons inwards into this. When we go through and look at this drawing, you'll notice that that hydrogen, with its hybridized, or that carbon's sp3 hybridized orbital, is aligning with the pi bond. Okay, why does it need to align with it? To get a pi bond, we have to have overlapping p orbitals. So if I've got my p orbital on my carbocation and my sp3 hydrogen, can I form that bond? No. The only time that I can form that bond is when what? I rotate about that sigma bond. Remember, it's still a single bond. I can freely rotate that. I can rotate that bond until I get the perfect alignment between the hydrogen and the carbon. And now the hydrogen can get popped off, the electron density falls in, and we form that pi bond. Only at the instant that those orbitals align can I get that elimination to occur. Which then begs the next question. Is it possible to prevent that alignment? Yeah. We can potentially sterically prevent that alignment or weaken its ability to align appropriately, which is going to drastically slow the reaction if we can set that situation up. Hi. Is it as important for the E1 type reaction? What's special about that single bond? It can freely rotate. Which means in the case of the E1, because I've got that carbocation, I can sit there and spin until I hit that proper alignment. Boom, now I can do my elimination. Okay? Really isn't a big issue with that. That cation's already at a high energy state, and I can allow that thing to rotate like a propeller until it hits perfectly. Okay? So now the next issue that we're kind of getting into. Why is that carbon-hydrogen bond broken? Okay, and we looked at one option. We looked at no difference in electronegativity. So it's not a polar bond, which by definition is also going to mean it's not acidic. So how can I get that bond broken? I have to provide energy to get that bond to break. How do we provide energy? Heat. So what we can go through and do is add enough thermal energy, enough heat to the elimination reaction that bond starts to oscillate. If we add enough heat, that bond oscillates so much that it hits that proper alignment, and then the electrons get stolen away, and now the hydrogen has nothing to come back to and floats off into the solution, and we have our elimination. Okay? So a really big red flag that we're looking at an elimination reaction is heat. Okay? Could I have used something else to help break that bond? Could also go through and use a base. The base is similar to your nucleophile in the respect that it's donating electron density. Okay? Which means, which do we want to use for an E1 elimination? Do I want a strong or a weak base? Okay, which step is the slow step in my E1 elimination? The first one. Which means the strength of the base is going to do what to the speed of the mechanism? Nothing. Okay? So if I don't have to use a strong base, I'm not going to. Because all that's going to do is increase the danger that I'm exposed to. Which means when we look at an E1 elimination, just like with the SN1, instead of using a strong nucleophile or a strong base, we will use a weak base. Right? With our elimination reactions, those become even more obnoxious, particularly within the one type. We can have solvolysis and the substitution reactions. You get a similar issue with the eliminations. The solvent can act as a base and help pull off that hydrogen. Right? So be aware of that limitation or that issue popping up within your reactions. Okay? Both one-type reactions, the solvent and the reactive base or nucleophile, are or usually the same thing. Okay? Questions within the E1 elimination? Yes.
A weak base is a strong nucleophile.
What's that?
A weak base is a strong nucleophile.
You're overlapping leaving groups with that. So what you're trying to do is look at a weak base. A weak base is typically also a weak nucleophile, but not always. Okay? What can you tell me about iodide? Big, fair enough. We looked at I minus. Okay, so it's big, which means lots of electron density, which means it's also polarizable. What's the issue with species that are polarizable? Oh, I should have watched what I was doing. Come on, reconnect. Internets. If it's polarizable, it is a good nucleophile. Awesome. Lecture recording just died. Okay, so we'll leave that there. See if we can figure it out on its own. If we've got our I minus, polarizability just means we can push that electron density around. So with a lot of electron density, it becomes very, very polarizable. Okay. If it's polarizable, it becomes a good nucleophile. Okay. In this case, we expect it to be strong or weak. Why is it strong? Like 3 or 4 of you said strong. Oh. It's negatively charged, so we're looking at a strong nucleophile. How is its base strength? Why is it a very weak base? Nope. If it acts as a base, it forms HI. What is HI? Strong acid, by definition, dissociates the other direction. Right. So you can't necessarily say, bring in this weak base, strong nucleophile argument. Don't tie those together. There are certain species that are great as nucleophiles, but horrible as bases. One of them, your halogens. Halogens are fantastic nucleophiles, but horrible bases. Why? They're all strong acids. HCl, HBr, HI, all of them strong acids. So they're horrible bases, great nucleophiles. What's an example of a good base, but a bad nucleophile?
As a weak conjugate acid.
Nope. It goes to size. Okay, that's where we delineate. Because a nucleophile needs to get into anything other than hydrogen, whoops, whereas our base just needs to get to hydrogen. Where is hydrogen in a structure? On the outside of the structure. What's the easiest thing to gain access to? The outside of the structure. The nucleophile needs to get into the inside of the structure, which means it has to get by all the hydrogens, all those other bonds, which means all those other electrons. So if I want a good base, it needs to have, first off, a good strong base should have a negative charge, okay, but it now needs to be sterically hindered. T-butoxide, okay, which we just talked about. Or LDA, our lithium diisopropylamine. Okay? Because both of these have a lot of steric bulk that will prevent our nitrogen or our oxygen, that's not the right guy, from acting as a nucleophile. Prevents them from actually getting in there. So if you want a good strong base, make it big. Okay? Let's see, figure out what it was doing. No. Awesome.